Welcome to the third lecture video in our Class 14 series of lecture videos. This one will be a short one, so hopefully relatively painless. We're just going to talk briefly about nucleophiles in the SN2 reaction, do a little, comparison of factors that can affect um, how they react. So let's start with methoxide. So methoxide's kind of like hydroxide, except instead of an oxygen-hydrogen bond, we've got an oxygen bonded to a methyl group. They have similar relative basicities. Methoxide is just about as basic as hydroxide. So here we have methoxide, and we've thrown in methyl iodide. We have a good leaving group. In iodide, we have the least sterically hindered methyl carbon electrophile. We'll do our SN2 reaction. We get dimethyl ether and iodide. The relative rate is fast. What if instead of a methyl group, we have a tert-butyl group? This is sterically a little more crowded than a methyl group. So it somewhat protects the nucleophile, the oxygen, but not completely. So our tert-butoxide is a fairly strong base. It's actually a bit stronger than hydroxide or methoxide. We throw in methyl iodide. We still do an SN2 reaction. We get tert-butyl methyl ether or methyl tert-butyl ether, depending on which alkyl group you name first. We abbreviate this MTBE as a solvent. We used to put it in gasoline as an oxygenation component. It smells like coconut oil, believe it or not. This is a bit slower. It's still okay as a reaction. It's slower because we have a larger group hanging off of our nucleophile, our nucleophilic oxygen, and it kind of protects that sterically from being accessed by the methyl group as easily. So we've raised the activation energy. And I've only given you relative descriptors. How about something for which we know the actual quantitative relative rates? Well, here we've got quinolclidine and ethyl iodide, and we're forming tetraalkyl ammonium iodide salt. Quinolclidine has groups that are very similar to ethyl groups. So how about triethylamine and ethyl iodide to form tetraethyl ammonium iodide? Well, if this relative rate is 1, our quinolclidine reacts 254 times faster. Wow, that's a big difference. Why is this a better nucleophile than this nitrogen? Well, it has something to do with sterics again. So for our triethylamine, there are all sorts of conformations available on our ethyl groups. They're, free to rotate, and they might rotate in such a way that a methyl group might shroud this lone pair of electrons on our nitrogen of our triethylamine. Or, geez, all 3 ethyl groups might contribute to help shrouding that. Quinolclidine, on the other hand, this is another way of representing it in bond line, its lone pair of electrons is fairly exposed. So why is it exposed? Well, those ethyl-like groups are tied behind its back with that tertiary carbon joining them. So they can't wander out in front of the lone pair of electrons and protect it from the electrophile. So in quinolclidine, the alkyl groups are tied behind nitrogen's back, and the non-bonding lone pairs on the nitrogen are exposed, making that SN2 activation energy lower. If your activation energy is lower, your reaction goes faster, and that's reflected in those relative rates. So as we saw, 254 times faster than triethylamine reacting with ethyl iodide. So that does it for our brief comments on nucleophiles for this part of the SN2 reaction. I'm sure we'll talk more about the parameters than our basic introduction uncovered in this Class 14 lecture time, but we'll leave those for future classes. In our next video in this class time series, we'll talk about solvent effects.